one of the things you have to be able to do is apply what it is you've learned. This is gonna help you too. Did McBride get an answer sheet?
I did.
All right, everybody's got one, right?
I got two.
You got 2 answer sheets? Okay, you get to take 2 tests. I'll give you twice as many questions. All right. So, let's look here. Now, some of this is gonna sound like review, but it sort of fleshes it out in a minute. All right, so everybody's learned in Ohm's Law. You know how to calculate wattage too. You ought to be able to get better and better at what you're doing so you don't even really have to think about it a whole lot. And what an expert is. An expert has the ability to perform at a high level repeatedly, and that's what you're shooting for. Let me ask you this. What if you were told that the local hamburger joint will give you a 99% guarantee that there wouldn't be a hair on your hamburger?
What about the other?
99%. Like at 99 times out of 100, the hamburger they serve would not have a hair on it. Would that be good enough for you? All right, so if you're going to work for somebody, you say, I guarantee you that 99% of the time, I'm going to do my best. The rest of the time, I can't promise you anything. Well, I'm going to hire somebody else. You know what I mean? You got to be able to do that right there. Question 1. A 12-volt circuit is powering a bulb that's pulling 6 amps. What is the bulb's wattage? What is the bulb's wattage?
Oh, I gotta use my
Park your cell phone, Zane. What?
I gotta use my calculator.
A 12-volt circuit is you can do this in your head. 12-volt circuit is powering a bulb that's pulling 6 amps. What is the bulb's wattage? All right. We will move on now. We can't stay here too long or we'll run out of time. You don't use Ohm's Law very much in the day-to-day grind, but you need to understand it. You need to know what's going on with it. And if the dealer sends you to electrical school or things you already need to know, and Ohm's Law is just one of them. I remember whenever Jimmy went to electrical school, when he first went to Ford, he went up to electrical school, and it was just snap, snap, click, click, click. He didn't have any problem at all understanding it. And these other guys that had never been to any kind of training like what I'm doing here, he said, man, they were struggling. They couldn't figure this out. They were scared to death they were going to fail and all that kind of stuff. So he stayed through lunch one day and gave them a few pointers and softened everything up for them. I mean, I don't know, they were afraid to ask in class about it, but they were over there privately talking to him. And he says, the stuff the way that you taught it over there was just like the way they were teaching it at Ford, the boards and everything that I'm doing on. But anyway, question 2. A 12-volt circuit is pulling 6 amps. What's the resistance of the load? A 12-volt circuit is pulling 6 amps. What's the resistance of the load? That's question 2. 8 more questions to go. And they get harder as we go, so you got to be able to imagine this. What if this was your final, man? You know what I mean? Everybody's supposed to know this already, right? We're engineers. We need to know all sorts of things. If you're an engineer, you need to know how to do things. You need to know how to do mechanical things and electrical things. This is from one of those competitions where they put you out there in a junkyard with a bunch of stuff and you had to build something that would work, in just a few hours.
What do they got to run off that chain?
That's the throttle, man. See what? In order to make the throttle work, when you mash the gas, they put chains and sprockets and all that. That's pretty good engineering right there, I thought, And so that thing, you must have somebody on Facebook said, I bet it's got to be a heavy spring so the weight of that chain don't pull it from the throttle open, just the weight of the chain. That's pretty interesting. But the secret to success is going to be a solid mastery of the fundamentals. If you have been struggling with these questions I've been asking you, then you're having trouble mastering the fundamentals. If you get master of the fundamentals, you'll eventually become expert. You'll be able to where you can actually figure out and fix things right the first time. Fix it right the first time consistently. You remember that time that I was telling you about that expedition that came through there that whenever it rained, it was the horn and everything. They do crazy stuff. And some dealer down there had tried to fix it and couldn't figure out what was wrong with it, and they gave it to me. And meanwhile, the guy that's the representative from the manufacturer came, and they look at the scores of Fix It Right the first time for the whole shop. They're basically, you got to keep your Fix It Right the first time scores up. You're always chasing that carrot, trying to make sure that nobody came back saying, hey, I had to come back for the same problem and all this kind of thing. They put out surveys and all that kind of thing. And so, because of the fact that for some strange reason, and I wasn't even getting paid to do this, but I was always seemed to be the representative of the shop. If that guy wanted to fuss about our fix it right the first time scores, even though there was 24 other guys there, he would talk to me about it, like I had any control over that. I don't know what the deal was, but anyway, I called him. I went in there and I said, I found out what was wrong with your expedition, so now Ford's not going to have to buy it back. And I showed him he says, well, we need to talk about your fix it right the first time, Ford. I said, well, this is the first time I've seen this one and I fixed it right. What about these other people? Maybe you need to go talk to them, you know. All right, but anyway, question 3, conventional versus electron theory. Conventional current theory, flows theory says electrons flow which way? Do they flow this way or do they flow that way? Conventional. There's conventional and then there's electron theory. All right. Understanding voltage. Now, you got to understand voltage as well as how to interpret the test. Whenever you measure, this is like with a scope or anything else or a scan tool. If you look at readings and you don't know what they mean, somebody else may as well be looking at it. But if you understand what you're reading, it'll be good to go. So voltage is electrical pressure, so voltage is necessary for current to flow. Without voltage, no current will flow. So where there's no voltage, there's no flow. Now you got to check battery voltage first. So you check your battery voltage first and you make sure you got good voltage throughout the system. But at the origin of it, whenever you're sitting here without the engine running, it's going to be your battery. And I will tell you this, a bad battery or loose battery cable connection can make even a car, when there's nothing else wrong with it, can make a car quit going down the road if you got bad battery terminal connections. Seen it happen. All right, now voltage is the only command. Voltage is basically given marching orders. Amperage, color that current flow, does the work. So resistance restricts amperage and that reduces the amount of work that can be done. So if you're slacking it off so that it can't as much current flow, you're not going to be able to do as much work. Lower voltage requires more amperage to get the same work done. Now this right here is what happens, and we talked about this a little bit before, whenever you start building a little resistance, you get some oxidation because you get heat, and the more oxidation you get, the more resistance you get, and finally it snowballs out of control and you wind up with a burnt up connector. That typically happens on headlamp circuits, fan circuits, anything that pulls a lot of current, right? All right, onboard computers, the computers communicate only in voltage and not in amperage. Right? Now some of the computers will actually have a little current probe around the wire to see if it's charging, but all of that still, every time a computer takes an input, even an analog input, it's basically going to convert it to something digital, because computers like digital but they despise analog. They don't really have a lot of use for analog stuff. If an analog speed sensor PID reading flips back and forth between, see, this is analog and that's digital, so it has to take a reading like this. You know how it does that? You ever think about that? How does it take analog and change it to digital? If you were engineering it, how would you make it happen? There's a threshold. As when a voltage goes above a certain threshold, it considers it on. When it goes below a certain threshold, it considers it off. So it can actually take an analog signal and turn it into a digital signal. One of the very first things that I learned, the very first, factory school I ever went to, was the instructor on these early 80s GM cars, real early 80s. She was showing me, she says, this is these analog map sensor. The computer doesn't like that. It likes for them to be digital. And so it's going to change that. I remember hearing that, and ever since then, every time I've ever been in any course about computers, they always talk about it, takes analog stuff and changes it into digital. So anyway, if you got a bad analog to digital converter in your PCM, BCM, you may see a PID that's flipping and acting really weird, even though it doesn't look peculiar at the computer. A variable reluctance sensor produces what kind of signal? That's question number 4. What kind of signal is produced by a variable reluctance sensor? That would be like the sensor on the front of this engine here. Variable reluctance sensor. That's a magnet with balls of wire wrapped around it, 2 wires coming off of it, and you're basically reading that with a scope. What are you going to see? Scope tip. All right, the cam crank to vehicle speed sensors usually have an analog voltage, which is this, and it's important to remember the sensor's frequency pattern and signature are what the EC uses to determine a spinning shaft's input speed and Z. Now you got to remember, it's converting this to digital in its little innards, but it's also looking at that slope, because it can do that digitally. Triggering and slope come into play when it's interpreting a signal. So if you connect the sensor wires backwards on some sensors, it can confuse the computer, and on some it'll cause a no start. I noticed you can take the the crank sensor, and you can hook it up backwards on this little board over here. Hook your scan tool up to it, and when you start that board spinning, your RPM on your scan tool will go up to about 200, and then it'll drop to 0, and you'll never get a spark. Because it knows you got those wires hooked up backwards because it's looking at the slope. Got it? You could do that, if you wanted to be really mean and ugly and nasty, you could basically take the two pins loose from the crank sensor and swap them around, put them in there backwards. It would take weeks for somebody to find that. Unless they were familiar with it and they looked at it with a scope and they noticed the pattern looked backwards, and then they say, well, that's polarity reversed, you know. I've actually seen one where the signal was there, but it wasn't quite strong enough, and it wouldn't fire. It was on a Ranger I was working on, and I had an EDIS module in my toolbox that was one that I kept for testing, and I plugged it in and it still wouldn't start, and I hooked the scope up to it, and I had me a really good pattern there, and I said, what the heck is this, you know? Although I was looking at a pretty good amplitude, didn't look bad to me. So if it's got everything else it needs, why is it not firing the coils? And why is it not, you know, sending any signal out, reference signal, so the computer can operate the injectors? And just out of desperation, I said, let's just rake everything else on the table and see what we got here. So snip, snip, I cut the wires, made me a twisted pair using a drill and a vise, put some foil tape around it, it had a ground wire in it, and I actually connected it from an overlay from and that's basically just threw it across the engine over there to start with, hooked it up between the crank sensor and the EDIS module, and it fired right up. And then about 4 or 5 weeks later, this guy says, hey, I've got one down here that's giving me a good signal, but it won't crank and all that. And I said, run you an overlay and see what that does. And I heard it a little bit later go, whoom. I've only seen that 2 times. I mean, other people might have seen it. But see, the thing about it is, what you don't need to do, I did not have the luxury, and sometimes whenever I would call the hotline, the people, the engineers up there, they didn't know what to tell me. So I'm on my own. I didn't have anybody to ask. I didn't have a guy in the next stall to ask, because they were always asking me stuff. You know what I mean? Have you ever seen somebody you don't ask because you know that they're probably not going to know the answer? You know what I mean? You hear where I'm going with that? So this is on me. I got to figure this out. All right, so computer output signals are always digital. That means on or off voltage triggers. All right? So the PCM sends digital triggers in several different ways. Pulse width modulation, on time, as well as injection. Notice this, 90% duty cycle. See, if it was always up here, that would be 100% duty cycle. If it was always down here off, that will be a 0% duty cycle. When it's 10%, that means it's on 10% of the time. If it's on half the time, that's 50%. You understand what duty cycle is? You got that? Don't forget that, because there are times whenever, and also incidentally, when they turn off the injector, you're going to get nearly a 50-volt spike. So if you're checking injector pulse on a scope, you need to set the plus or minus 50 volts, or it's going to go off the screen. And that's what an injector looks like on there. Computer output signals are always digital, right? So duty cycle and pulse width are practically the same thing, but dash lights on some cars and some solenoids are duty cycle on newer cars. Like, what about whenever they duty cycle it, on sometimes it will actually put out more and more of a duty cycle to increase the amperage, which is a way that it does, work with amperage going out. And it can do that on variable force solenoids and transmission pressure circuits, and it also does it with your, Ford does it on your idle air control. And so that's the thing. Now, what about yesterday you were hearing a solenoid going tick, 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 tick. What was that? Remember?
That was a canister purge valve.
Canister purge valve, and so you've also, and that's basically going to have a percentage of duty cycle if you look at the scan tool. What about your torque converter? If your torque converter lockup it doesn't just go to straight lockup like it used to. It goes to 10, 20%, 30%, 40%, 50, 60, 70, and then 100%. It actually goes up by percentages, and it's dithering that thing. And the first time I ever run into that was on a fighting with a surge problem on an '89 Eagle Summit that was not my very old car, and it was doing some crazy stuff that initially I thought was engine related, and then I put a dwell meter, which is what you check to dwell on points with, and I hooked that dwell meter up to the doggone torque converter lead coming out of the computer, and I could tell that it was putting more, watching that dwell meter, I could tell this is a modulated signal, because I was used to him just being a straight lockup, you know what I mean? All right, so anyway, but pay attention to that, because there's a lot of them things that are doing that. All right. Computer output signals are always digital, like I always said. Don't forget that frequency at which the cycle is repeating is this here, like this 1 second, and if it repeats 4 times in 1 second, it's 4 hertz. even some of the diagnostics we used to have, when they were talking about what the frequency of a flashing light would be, they said it was 1.8 hertz. You know, if you're looking at the flashing on like for example, on some of the old airbag systems on the old early 80s Lincolns, they would say whenever you're what you'd have to do is put it in a self-test, open the door and close it, and that would throw it in a self-test, and you watch it flashing, and it would do crazy things like raise and lower the car and do all that kind of stuff. And you could, if it didn't raise and lower the back of the car, you'd know that something was wrong right there and all that stuff. But they'd say it flashes at 1.8 hertz. A Hall effect sensor produces what kind of signal? Put something down on your paper, don't leave it blank. All right. Any answer is better than no answer. Practice makes perfect. Now, hone your troubleshooting skills by using a scope to view inputs and outputs. You gotta have the eye of the tiger, man. You know, take stored captures and share them with other mechanics online. It helps if you got hooked up to the Pico website. You know, you can actually, if you got a Pico scope you're working with or any other kind. Like for example, on the Facebook page that I'm a part of is Automotive Scope Diagnostics, and there's all kinds of cool stuff that you can see on there that gives you information. And if you go on there asking. If you've got a subscription to IATN that's the bottom tier subscription, you can actually usually get scope patterns from there. Like if you're looking at a cam and crank signal on a particular vehicle and you want to see if it's right, you got to go track that down. Identifix sometimes, if you've got a subscription to them, you can actually call them and say, hey, I need or send them an email, so I need a scope pattern on this, that, and the other, and they'll send you the one that they've got on file. It really helps. Kirchhoff's law of voltage drop refers to the fact that voltage drops across a load, and a load's basically anything that has resistance. You got your bulbs, you got your motor. Loads have resistance, in turn current and heat, light movement, and bad connections also have resistance. Remember the importance of voltage drop testing. Resistance is also found in places we might overlook. You can see some places where you can't see it. Basically, you're not always there. There may not be enough voltage drop to cause a heat damage. It may just be dropping voltage enough to work, whatever it is. I found a crazy situation one time where over there at the VIP test connector, the self-test wire is supposed to be shorted to ground, the little one's by itself. I'll show you that tomorrow. We'll talk about that a little bit. But if I had one that would not go into self-test. I mean, everything was running and all I needed to get codes that I wouldn't go into self-test. And so I get my meter and I go over here and I'm checking that single wire, and I'm seeing 2 volts there. And so I go over here at the engine controller and I check and I got 5 volts there. And so I went back to the end where I was supposed to ground it to pull that 5 volts to ground, and it was 2 volts again. So I went down the wire, and the closer I got to the engine controller, the higher the voltage got. That was plumb weird, it's just strange as all get out. And there was no load on that wire either. That's the kind of stuff that just doesn't make any sense. And I used to see stuff like it every now and then. I don't know who could explain that to me, but I ran another wire. There's something going on with that wire. I don't know what it was. I ran another wire over and took care of that problem. But anyway, all right. Question 6. The left headlight is dimmer than the right one, but the bulb is new. Where would you connect your voltmeter leads to do the first voltage drop test on this problem? And you see these numbers here, right? Where would you connect your voltmeter leads to do the first voltage drop test on this problem? This headlight's dim. This one right here. If you were you say, now we're going to see if we got a voltage drop problem, where are you going to connect your meter?
Between the left and right and left.
Well, you think you're dropping voltage between those two? That's an odd place to put it. See what I mean? Isn't it disgusting when somebody gives you short answer test and not multiple choice? Well, you got to think, man. That's what I'm trying to do. I'm trying to get you to where you can think.
Is it both low and high beam for Jim?
Yeah, well, on that particular, that's a good question, Nate, it really is. On that particular light, let's see, I'm going to say that let's say that just the low beam is, for our purposes, we'll just say that just the low beam is dimmer, but the high beam seems okay. High beam's just as bright when you put it on bright, but it's dimmer on the low beam, and you've already replaced the bulb. And the bulb don't know what's wrong with it. And basically, you'll see if you're dropping voltage, right? So where would you connect your meter? You know how to do voltage drop. It shouldn't be too hard of a question. We're going to try to whip back through these right quick and tell you what tell you what the answer is. All right, question 6. The voltmeter reading is 3.8 volts when the starter's engaged. You see where we're hooked up? what, if anything, needs to be done? The voltmeter reading, when you engage a starter and you got your meter hooked up, the voltmeter reading is 3.8 volts when the starter's engaged. What do we need to do?
I thought the other was question 6.
Yeah.
Maybe it was. We may have 11 questions. You may have to go off the bottom of the page. Yeah. Hey, I did this when I was in a hurry, okay? So I wrote this. This is not, you're on the first ones that ever seen this PowerPoint presentation. So just move on. You may have to move, you may have to bump your answers down. We'll figure it out. What needs to be done? Hey, don't focus on that, focus on this and that. What do we need to do about that? We're spinning the starter, we're seeing 3.8 volts right here. Moving on. Okay, an engine controller takes advantage of voltage drop by reading the voltage after a fixed resistor to determine the resistance and temperature of the coolant temperature sensor. See, you got a resistor in here that changes, and this one right here is a fixed resistor, and so it's basically reading off of that. I mean, the engine controller is reading off of that. All right, now your variable resistor right there is the one that's going to change. That's the one that changes right here. So it changes, provides a change in input, and that's a negative temperature coefficient. Okay, dynamic rationality testing. Now this is cool stuff. This is not a question, but this is something you need to know. You scope the signal wire of the mass airflow circuit, both at the, so you can edit the voltmeter either, both at the sensor as well as at the engine controller. Since the mass airflow voltage originates at the sensor, see, it's not coming from the controller, it's coming from the sensor on a mass airflow sensor. So the origin of the voltage is an important thing to note. On an oxygen sensor, the voltage is coming from the sensor itself. On an engine coolant temperature sensor, the voltage is coming from the computer. See, so you gotta know where it's originating from, you gotta know how the sensors work. All right, so since the mass airflow voltage originates at the sensor, a lower measured voltage at the PCM can be an indicator of mass airflow circuit problem. Not sensor problems, circuit problems. If you're getting a good reading here and a lousy reading there, something's wrong in here. You got that? All right, Kirchhoff's law refers to what? We talked about it 3 slides ago. If you were listening, you'll know. That's why I'm giving you a test nowadays, so I know you're not just tuning me out, waiting for the lunchtime to get here. Okay. Kirchhoff's law refers to what? Parasitic draw testing can be a kind of time-consuming task. You wait for modules to go to sleep and connect or disconnect circuits. Takes a lot of time. So, what's the amperage rating of this fuse?
Ooh,
You should have those mesmerized. All right, so parasitic draw testing, you can take this right here, you can take your 2 meter leads, you can touch to both sides of all these fuses. First, you find the fuses that have power, that are 2 of them, right? And you remember those. And then you go to each fuse that's got power to it. You don't need to check the ones that ain't got no power to it anyway. And then you do voltage drop across the fuse, because every connection is going to have a little, current loss. And so if you check all of those fuses, the ones that are hot on both sides, the one with the most voltage drop is probably going to be the one where your draw is. You got that? Now it's going to be a small amount of current drop, I mean a voltage drop, but when you measure voltage drop across the fuse, that means current flowing there. You can also take your forward-looking infrared camera and shoot it and see where the heat is. All right. You can eliminate the fuses with no voltage drop very quickly and narrow the circuit for the drain down to the fuses showing the highest amount of drop. And see on these how they pop those covers off so they can do those? You know how they get that little window there? They basically took those little covers off all those, plugged them back in, let it power back up. All right, amperage traces taken with an inductive meter provide a lot of information about what's going on in a circuit when diagnosing electric motors, solenoids. Scope and voltage and amperage on the same injector provides a view of the command as well as what happens. See right there? That's where the panel starts to open on that. And that's pretty cool stuff right there. Voltage waveforms are captured using what kind of probe? Voltage waveforms are captured using what kind of probe? How do you hook up if you're going to read a voltage waveform? Amperage waveforms are captured using what kind of probe? All right, take your job seriously. Always learn. You're always wanting to be learning, right? All right. Take every opportunity to learn and improve. Don't be lazy. If you don't like work, you're not gonna like any job. You know? There's no job that doesn't sometimes feel like you're in a rut. I don't care what kind of job you got. There's gonna be some days you feel like you're in a rut, right? Can't you guys tell that sometimes I get in a rut around here? I mean, I'm so excited all the time, you know?
You put this on your face.
Get used to, hey, don't start with this. Get used to having days like that. Easy jobs don't pay well. You want an easy job? Don't expect to get paid well. This parts guy one time was grousing because the parts I needed him to look up were so hard to look up. I said, how much do you think you'd get paid if all you had to do is go back to the parts room and get 2 boxes, A or B, and put them on the counter? They could train anybody to do that. All they got to do is be able to recognize an A or B. You have to look in this computer and you have to find the part that I need and you have to give it to me so I can fix this car and get out of here. They pay you to do this and that's why they pay you as good as they do. So shut up and do your job. Well, that was kind of a wake-up call. He shut up and did his job. All right. Nobody owes you anything you didn't earn. If you didn't earn it, they don't owe it to you. You got it? You understand what I'm saying? No. Okay. Now then, we're going to back up. We're going to look at these questions right quick. We got a little time. All right. Let's go to. We're going to have to go quick. All right. What's the answer to that one?
72.
Huh?
72.
72. I'm going to multiply
12 times 6.
6 times 12. 72. 72. You go, boys. All right, wait a minute. Let's go to the next one. What's that one?
2.
What is it?
2.
2.
4,
All right.
6, 8. You missed one, this one.
Uh-oh. Did I miss that one? Missed 3. Oh, yes. Which way does conventional theory say current flows?
Positive and negative.
Yeah, conventional theory says that. Electron theory says it goes the other way. That's a good point. Variable reluctance sensor produces what?
Analog.
Analog. One of those, right?
I thought you wanted us like what it looked like. You drew this. I drew it.
Yeah, that's okay. That'll work. You can do that.
But it's probably wrong, but I drew it.
No, you're not going to get it wrong. A Hall effect sensor produces what?
Digital.
Huh? Digital, square. It's a square wave. Like that. Right? All right. So, question 6. What would you do here? I tell you what I do. Let's say it's a low beam. The low beam is going to be this one right here. I'm going to go from the positive side of the battery to pin 12 with that light burning.
Yeah, I was wondering.
I'm going to go from the positive side of the battery to right there. Now, until I track it down, if I find voltage drop there, I'm still going to have to go and find out where it is in here. But I can actually follow, I could actually say, like if I got a bunch of voltage drop here, like if I only got 6 volts here, then I could back up and go here, and then I could back up and go there, and back up, so you go through that and all that. All right, so this voltmeter reading is 3.8 volts when the starter's engaged. What do we need to do? Anybody even know?
You replace it.
I would, at the very least, put a starter solenoid on it. Because that copper washer that's slapping against them 2 big studs in there that gives the energizes the starter, there's voltage dropping between there and there. That's got to be a solenoid problem. Of course, like Zane said, changing the starter is better because usually the solenoid is too expensive nowadays to even replace. But you could replace the solenoid and get it done. All right. All right, here we go. Kirchhoff's law refers to what?
Direction of current.
Voltage drop. That's talking about voltage drop. Question 8, what's the amperage?
5.
25. A natural fuse is a 25 amp fuse. All right, 5 amp fuse is,
Oh, I said 25.
yeah, 25, that's right. All right, now let's go here. Voltage waveforms are captured using what?
Voltage probe.
Just a plain old probe. Yeah, you just hook into the wire, right? And then, what you get with this?
Amperage.
Yeah, you're gonna be the one that goes around the wire, an inductive probe, right? And so, how'd you do? You do pretty good?
I missed like one, to be honest.